Well, yeah, let's get started. Um, so yeah, this is a discussion on Zephyr's port to the Xtensa architecture. Xtensa is a I'll get to that on the slide in just a moment. But the intended audience here is anyone interested in weird just stories about oddball CPU architectures that you may not have known before. It might be helpful to anybody working on architecture ports in other environments to see some of the tricks that have to be played when you bump into, again, idiosyncrasies. So the content is going to be, like I say, all over the place. It's as much vignettes and stories as it is organized technical content, and the detail is going to be on the low level side, just to give folks a warning. I mean, if you're comfortable talking about assembly language, you're going to have no trouble. If things are getting a little too far into the weeds, just give me a hands up, and I can up level and provide more context. Some of this stuff again can be obscured by the fact that you work with it too long and you forget that people are working on different environments. So who am I? I'm Andy Ross. Pleased to meet all of you. I do see a lot of familiar names in the chat, though, so I think I've met most of you. I'm a software engineer here at Intel in Portland, Oregon. There's some contact information down there. As far as the Zephyr project, I tend to be, mostly hiding in sort of the guts of the core kernel. This talk obviously is about an architecture. My other responsibilities sort of include the scheduler and timing subsystem, little bits of the driver model that interact with those guys, some of the IPC primitives, and then bits and pieces here and there, some of the data structures and the heap code and that sort of thing. So I'm a good source if you need questions about, arbitrary, crazy low-level details. Not necessarily a great depth source on anything, but the kind of couple areas of expertise. For those of you interested in more stuff that I do have a scheduler talk coming up tomorrow, which is a somewhat higher level application focused thing on scheduler APIs and how they work with real time. So let's get started. Let's talk about Xtensa. So I suspect most people here are aware, but Xtensa is a CPU architecture that is not as new as you might expect. It's been around for quite some time. It was originally invented by a company called Tensilica, since acquired by Cadence. And it's not a newcomer to Zephyr either. We added support really a little over 3 years ago for the expressive ESP32 device, which is a sort of a popular hobbyist device. It's got great Wi-Fi support, and it was and notably it had 2 CPUs, and which is the reason we ended up picking it. It was in fact the very first SMP device on Zephyr. Closer to home, it's also the device that was picked for the Intel Audio DSP I believe originally in the Bay Trail platform, one of the tablet chips we had going on almost 8 years ago now. So it's been around the block within Intel for a while. People here are reasonably familiar with it. It has a bunch of advantages for applications like audio DSPs. I know there's a newer NXP chip that was actually just released that would be great to add to Zephyr, and I think there's some work going on that, which is actually a very similar kind of architecture. As we also have the Odroid Go entry. I know nothing about that other than it's a Game Boy emulator, but it's a pretty cool looking device. It looks like you can't buy them anymore, which is unfortunate. But there is support in the tree. I don't know how mature it is. It's a wonderful thing about community projects is you can go in and start writing your slides and just do a quick overview of different platforms and realize that I've never played with this thing. It would be fun to look at. Xtensa is a fundamentally sort of configurable DSP. The idea is that they give you a big toolkit that contains a bunch of check marks, and you can control all sorts of things. You can write your own instructions. They have a sort of formal description of the various buses inside the CPU. This is a little out of scope for this talk because I'm not a hardware developer, but people with complicated hardware integration needs can latch onto this architecture add all kinds of different things to it that are visible directly to software. They don't need to talk to it as an I/O device, which makes it a great choice for things that have ISA extension needs, like vector DSPs is a great example. I know that there's some noise being made in the machine learning world too, although I don't actually know anything about any of those products. If you need to have something that needs its own register set and its own instructions, a coprocessor style device, Xtensa is aimed right at you, and and the side effect, of course, of that is that it's licensed really as just the customer configured IP, right? Like you go to their configurator, you push the buttons that you need to push to generate the CPU that you would like. It spits out a bunch of the RTL code basically that you can then hand to your hardware team to synthesize. But as a side effect, it means that there's just no single Xtensa CPU model. All kinds of things can change between two CPUs. The state that the CPU tracks and that needs to be managed by as a single context actually changes depending on who instantiated the CPU. And this has side effects downstream too. Their model is that the toolchain is specific to the CPU being instantiated. When you again have pushed your buttons and gotten back your package of synthesizable stuff, one of the things you get is a patch to GCC basically that allows you to build your own toolchain for your device. The side effect there, of course, is that every device that we have in the Zephyr tree in theory needs its own toolchain, even though in most cases these aren't very different. We've made some effort to try to unify those within the audio DSP just because we have more visibility into that, but it would be it's a real hardship in this world, and it would be nice if some toolchain work upstream would happen to try to do that more configurably. Moving on, just to give you the very rapid, I'm already running behind here, so I'm going to try to speed up. Very rapid just overview of just the basics of the architecture. Xtensa is like almost everything else Zephyr runs on, except x86. And, it's a traditional pipelined risk system, right? You've got load store style instructions. It's single issue. There's no out of order execution or parallelism inherent to the ISA anyway. It is in order. It exposes a symmetric set of 16 general purpose registers, just like 32-bit ARM does. They're named A0 to A16. A1 is a stack pointer, mostly by convention. We'll get to them later. There are actually a couple of instructions that do do deal with stack pointers directly. It has what actually is a fairly primitive interrupt handling architecture. There are 32 numbered interrupts. You can take those interrupts and they live in a bit mask in a particular register, but in fact they get muxed onto a fixed number, configurable number of priority levels. And where other architectures have their, like a lot more like x86, for example, has 256 vectors that are split out into 16 different priority levels. Here, that mapping is fixed and essentially arbitrary. So really what you have is some fixed number. 7 seems to be a popular number of interrupts that actually get handled at runtime. And I'm not going to talk about this too much because the details actually aren't that interesting. But level 1 turns out to be shared with exception processing, and that's a historical thing. Very early Xtensa systems had only one interrupt, and so you would have a if at the top of the interrupt to check one register and say, this is a divide by 0 exception, or a memory fault, or a some other instruction trap like a system call, or it could be an external interrupt, and you would actually handle those in the same path, which is somewhat unique to the architecture, but like I say, not really super interesting. And now we get into the sort of weirder stuff. Xtensa is, if nothing else, not strongly bound to convention in the rest of the technological industry. They really like doing things their own way. They have a lot of ideas that are really very clever, but in a lot of cases extremely strange for those of us coming from more conventional architectures, and especially so because in so many cases these are idiosyncrasies that end up specific to some device. If you don't instantiate this particular feature, you don't pay the complexity cost. So it's possible to write code without even knowing about this stuff, and then you go to a different system and then you trip over it. So one is that they have an abstracted idea about external CPU state, right? I mean, you've got general purpose registers, you've got, the rest of the stuff that in another CPU would be like spread around all kinds of things, right? On an x86 CPU, right, we've got MSRs and we've got the E flags register, the R flags register now. We've got state in the hidden registers that are loaded when you load segment descriptors, that sort of thing. In Xtensa, all of these are unified. They use a single API or a single instruction pair to read and write them, RSR and WSR, state registers. They have a byte in the instruction that specifies the register you want, so you have a space of 256, which isn't huge, but it's enough. And one of the nice things about it, it is, easily enumerable. We can just sort of sit there with a mask of like, hey, we know what special registers are out there and we know which ones need to be saved in different contexts. And it's easy to generate code to do this. I have to take some of that back because the assembler syntax doesn't actually allow you to do this via a straightforward number. You need to know what the name is, and that's just the way they've done the toolchain. That's unfortunate, but it's a resolvable problem. And the existence is exposed by system headers. The core ISA.h is the big one that gets generated by their toolchain patch generator. And is just a straightforward C header with a bunch of, I have this feature kind of things. So you can, write nice if-defy code to test for all kinds of notable things about the CPU configuration against which you're building. And that, again, is distributed as part of the toolchain notionally. In Zephyr, we've actually modified that a little bit. We have a small HAL layer for each of the different Xtensa platforms that has a copy of this file, precisely so that we can unify the tool chains. We don't need 17 of them. Some examples here, there's a program state register that is very similar to the E flags register in x86. It contains, most importantly, the current interrupt level for masking. It contains the register window state stuff and that sort of thing. Well, we'll get to some of that later. Xtensa has a loop instruction, which is a slightly CISC-y, a very low overhead counted loop kind of thing. It uses some special registers to do its job. The atomic test and set instruction, we'll get to that later too, has a scompare register that it uses as the operand. And again, this has to do with the fact that Xtensa is a fairly tight, 2-argument ISA. It has, tiny little 3-byte instructions. There's not enough registers in the ISA encoding to have 3 registers for a compare and set instruction. So they use a special register to do that. And a very similar thing for shift and rotate. There's a separate register that stores the rotation amount that you're going to do to use in the instruction, which is a total booby trap, by the way. We went for months with the SAR register there not being saved in context. We had a similar bug with scompare too. And with SAR, it worked because, if you don't happen to take an interrupt in the 2 instructions between setting SAR and doing your shift, you're fine. It just so happened that we have a crypto test suite in the Zephyr that was able to detect this because, needless to say, crypto does an awful lot of shifting. And so it would fail. It would fail spuriously. And eventually we figured out what was going on. So again, there's some things to watch out for with this architecture. And here I am noting, I actually already discussed this, that there is one tool chain instantiated for every single CPU. You change one thing with your CPU, and notionally at least you then need to rebuild your entire tool chain and ship a different one. This is in the commercial embedded world, it really is not a big hardship. Everybody has basically just picks one piece of hardware and starts writing code for it, and that's the way the industry works. Zephyr, we actually ship an SDK, and so a big chunk of the Zephyr SDK right now was needless duplication of all of these Xtensa tool chains. And we have register windows. So this is a feature that Xtensa didn't invent, right? I mean, Spark was doing this, way back in the late 1980s. And it's basically an echo of the idea that eventually became register renaming in more modern architectures. The idea is that registers are not expensive in hardware. It's easy to have lots of them. They are expensive to write to and read from memory. And they're a little bit expensive in instruction encoding to have too many of them, because that makes your instructions bigger if you need to encode 128 or whatever registers. So the idea is that you have a lot of registers within the CPU, and then you slide them in and out of a window of which ones are visible at a time. So the way that Xtensa works is you can instantiate your CPU with at least 16, because that's what the ISA has, but also 32 or 64 possible actual physical registers. And you can rotate them in groups of 4, so that if you're looking at a situation where you've got a function that is using registers A0 through A7 and not touching the top 2, you can make a function call by rotating only the 8 registers that you're actually using. And there are separate call instructions to do that. There's a variant that saves 4, a variant that saves 8, or one that saves 12 instructions. You do need to overlap 4 registers, obviously, simply because you need to be able to pass arguments and get a return value, right? I mean, there has to be some overlap between the function and its caller. It is a cyclic buffer, so if you keep pushing registers onto the stack, you'll eventually get to a situation where you need to use registers that are actually already owned by somebody up the stack that called you. And this is managed with exception handlers, basically the same way it is in Spark, but not the same way it is in Itanium. Itanium had a hardware stack engine instead. Here we take the complexity in software, and it's not that bad. Xtensa actually gives you code for these exception handlers that is basically as fast as it could possibly be, and everybody simply uses that. So the idea is that if you're trying to touch a register, and this happens at register access time, you'll actually trap to an exception to spill the register from the spot where you're trying to write or read, and then come back to you in a situation where that's no longer used. It's now been spilled out to the stack. And likewise, if you're trying to return and your caller happens to have been spilled by a previous thing, it will trap to an exception to refill those registers before you do the return. And this works. It actually works really, really well. The exception handlers to do this are no more than a few dozen cycles at most, and that's for the ones that need to actually trap 3 times to spill 3 different windows. It's really pretty clean, and it gives you almost zero overhead for stack management. All of it happens in the exception handlers. You never need to spill and fill in normal code, unless you're right. The compiler's generating a giant function that really has a bunch of local state that it needs to make space for. And in theory, it makes for faster function calls, right? I mean, everything really should work. Problem is, if you actually look at what's happening, the generated code for this stuff really isn't very good, and that's especially true of GCC. Xtensa's compiler does a little bit better on code size, and the reason is that it's this problem we're trying to decide: how much register space should our current function use? That's a global decision, right? I mean, the answer depends on who you're calling and what their needs are. If you're calling tiny leaf functions, you can use lots of memory. If you're calling things that are much deeper call stacks, it's much more useful for you to use, an optimized stack that does a little bit of manual memory management just to save the window space. But compilers just don't do that in the modern world. And to the extent that they are doing global optimizations, they're doing it in the context of like the modern link time optimization stuff, where their model is no longer about stack-based calls at all. Their model is that we're going to eliminate all those calls and inline everything, or inline almost everything. So in practice, the truth is extensive function calls are actually very expensive. I mean, especially in memory. I mean, extensive functions tend to be extraordinarily wasteful of the register windows that they use, just because the compiler assumes it's running in a context where, like other systems, you've got 16 registers, and 16 registers means 16 registers, and I can use them. It doesn't have a good model for when not to use that stuff. And like I say, there is a proprietary compiler sold by Cadence. It's actually being revved right now. There's a newer version based on Clang. The older one is based on the older GCC or GPL v2 GCC. And just the last note here, I'm actually not going to go too far into the hardware details of how this works, but it is super clever the way that they have been able to make these traps happen that quickly with almost zero hardware state. There's a group of 16 bits in the PS register that contain 16 bits plus a 2-bit rotate number that contains all the state you need, and all the tests that happen are just simple bit operations based on that and the register you're touching. It's really very clever. And I am okay. I'm catching up a little bit now. So let's go on to interrupt handling. Next topic that is something where Zephyr actually starts to need to play some tricks. Hardware entry in Xtensa works mostly like it does for any other architecture, right? I mean, you've got a fixed table of interrupt handlers. They have a few instructions of memory in the table, and then you're expected to do something, one or two things, and then jump out of the table to handle it. We mentioned earlier there are a small integer number of these interrupts. 7 seems to be a particularly popular number that's shared by both ESP32 and the audio DSP. So they just jump to whichever one corresponds to the interrupt that you've taken. They'll then mask off that interrupt, so you can't be then preempted. They have 2 special registers that are associated with each interrupt: EPC, which is the interrupted program counter, and PS, which is the state register that represents the interrupted code. They don't otherwise touch any CPU state. They just jump to your code. And then helpfully they provide this exe save scratch register, which allows code to play the musical chairs game that needs to play on interrupt entry, so it doesn't necessarily need to change stuff on the stack or wherever. Zephyr actually does not use this, or rather we use exactly one for all of them, and it comes later. We'll talk about cache coherence later. Which is actually a fairly helpful trick, which gives us access to all 7 of these exe save registers as scratch for other purposes. And again, we'll get to that in a bit. And so then, of course, Zephyr takes over, and like any other architecture, we've got to save contexts. And now we've got a problem with Xtensa, right? Because, well, Zephyr has like most operating systems, has a separate interrupt stack. There are good reasons for this, so that you can do better memory management and so that you can handle nested interrupts in a context where you can provably know what their stack usage is, so that you can size it so you'll never have an overflow, that sort of thing. The register window paradigm that we've discussed, assumes everything is being spilled out to the stack. They have a fairly complicated ABI for where registers go when they get spilled by those exception handlers. Well, that I guess means that we've got to spill all 64 general purpose registers on interrupt entry, and that's actually really expensive. This is indeed what the Linux, there's an Xtensa Linux port, and this is indeed the way that the Xtensa Linux port works. And I guess for Linux that's probably more tolerable. Linux is not as real-time an environment and doesn't have those kind of requirements. But again, we're operating in a situation where we're doing. I mean, again, at Intel, we're using this for audio processing, which is a hard real-time environment, and a couple hundred cycles on interrupt entry actually does matter. So, is there any way we can fix this? Well, yeah, we can. You can sort of very carefully, if you draw pictures between what's going on. You need a first call frame which is going to contain a spill area for the interrupted caller. Well, let's assume we're not going to spill the interrupted caller. We're just going to continue calling it as if it was calling somebody else, and we're going to give it a stack frame. So we need 4 registers for that. We need another 4 register frame that is going to contain a new stack pointer. Right, so that you can return from this one and recover the first stack pointer without having them live somehow in the same address. There actually are. If you check the comments in the assembly code here, you'll find a really dirty idea of mine where if you change the way the interrupt handlers the exception handlers work and store 1 extra bit of data somewhere to tell the difference between this kind of special frame and the regular frames, we actually could get rid of this, but we don't currently. We push 2 4 register frames onto the stack, or onto the register stack, the Windows stack, and then at that point you're okay. Now you can just set your stack pointer, literally just write to the A1 register, change your stack pointer like you would with any other stack switch, call your interrupt handler, it can be just a standard C function, nothing special. It will run on that stack just fine, and then when it takes an exception, it will actually spill functions to the right stack always. User code, the interrupted user code will get spilled to the user stack. The interrupted kernel code will get spilled to the kernel stack. Those special things don't actually store any data other than those stack pointers, so we don't really care whether or not they get corrupted or not. In fact, the middle one does, or the second one actually does get arbitrarily, spilled with whatever happened to be in the register at entry. And now we didn't have to spill anything. In fact, all we needed to spill was the GPRs that were in use, right? Because those don't have you don't have a space in the Windows spill call stack until you make a call, until you are no longer the active function. So we just have to spill the 16 registers that were in use at the time of the interrupt. And even that we don't need to do because the CPU has state that tells us which of those 16 registers are actually in use. I can check a bit mask. So in fact, if you interrupt a function that was only using the bottom 4 registers, you only have to spill 4 registers. This actually works surprisingly well. It means that interrupt entry is about, my original estimate was about 150 cycles quicker than doing the full GPR spill. And even in the case where you've been interrupted and you call into a very deep kernel call tree, right? Like you got some driver that needs to do something, huge. It obviously has to, right? It's going to spill all those interrupted things, but they're going to be spilled naturally. It's going to be spilled with the same overhead you would have if you were just making regular function calls. The overhead is effectively 0. And the only overhead you then need to take is to unspill them, to refill them into the situation after the interrupt. And that happens again via a natural code path, which works the same way it does otherwise. But it works at interrupt exit. And in fact, in most cases, it actually works after interrupt exit when the restored code gets to do its exceptions. Which means you're now taking the latency penalty in a situation where you don't have latency requirements. You're taking it in user code. So we're really pretty proud of this. I think this is one of the neater tricks. It's one of these things where, an architecture, kind of gives you lemons, but in a very clever way. They sort of gave you all the tools we needed to have to make this work fast. And like I say, I'm really pretty pleased with interrupt entry. And then we have interrupt handling, and I'm not sure we do this quite as well. I mentioned earlier that interrupt handlers are just C functions. You call them like C functions. That means you can write them in C. Well, let's write them in C. C code is good. Compilers are really good at generating optimized code. So one problem you have, of course, is that Xtensa has this notion of there are 32 numbered interrupts, and they're muxed onto these smaller number of things. So why not we know when we enter interrupt level 3 that there are only 4 different interrupts that might mux to this level, and one is a timer interrupt. Timer interrupts have different ACK, EOI handling. Basically, there's an interrupt acknowledge register you need to use for regular hardware interrupts. The timer interrupts you acknowledge by writing to the comparator register, and then software traps you don't need to acknowledge at all. And so there's different variant exit paths for each of these. But we know all of that. We know all of that at compile time because all of this is just fixed with the hardware. So why don't we just generate just really simple C code with a Python script, Xtensa in gen.py, that reads that core isa.h and generates exactly the minimal set of C code that you would need to handle each interrupt. And that sounds great, right? I mean, that should be basically optimal. There's we're doing the absolute minimum work. Unfortunately, it doesn't really work out quite like that. One is that, as I mentioned earlier, function call overhead is actually expensive. The compiler is not good at recognizing that you're generating this tiny minimal function and using, for example, only four registers. You totally could write these functions to run in just the 4 registers, from A0 to A3, but GCC just doesn't understand how to do that. In fact, they actually use more. They use 12 right now. The bit instructions on Xtensa actually turn out to be surprisingly slow. Remember that SAR register I mentioned earlier? Every shift and rotate instruction requires that you load this extra SR. And the real killer to this is that the limitations of the Xtensa interrupt layer, the fact that there are only 32 interrupts, which is not really that much for a big embedded controller. They have to be muxed onto exactly this set of priorities, means that all real world hardware tends to have some second level interrupt controller anyway. And of course we have support for that in Zephyr. We have an interrupt controller API. But if you're going to go through the trouble of, demuxing all of these things in C code in the interrupt controller, what are we gaining by doing it here? And the answer is basically nothing. So this is something I think we're going to need to fix at some point in the future. Like I say, we've done a great job of the first 40 instructions getting into the interrupt, and I think a fairly poor job of the next 90. But we'll get there. This is definitely something that can be fixed. And then having finished your interrupt, you've got to get out. And again, this doesn't look fundamentally different from other architectures. 8:33. All right, I'm not doing too bad on time. We call zget next switch handle to basically just get the next thread that we need to run. I will go on a quick digression here. Xtensa was our very first switch-based architecture. Because it was our very first SMP architecture, we needed to change the low-level Z swap API that is used for context switching on single CPU systems. And the reason for that is that the swap requires that you understand how to get the current thread, or the next thread, excuse me, well, the same thing in this case, out of the scheduler, from within the guts of the assembly code. And that's hard to make work in a portable way, because not all architectures can make C function calls. In that context, they may not have a stack, et cetera, et cetera. And Xtensa was one of those. So we invented this new Arch switch, which is a somewhat lower level primitive, where the switch, it's still a C function API, which is to say it's called out of C code as a function. It may be implemented as inline assembly, and it is on Xtensa. And it is presented with an opaque handle. Just here is your next thread to run, and then a pointer into which to store the saved context that you're going to save, and then it then never returns, or it returns when you then can switch back into the current thing. The CPU runs off to do its next thing. Anyway, so on interrupt exit, we use that same architecture to get a next switch handle. Again, the switch handle is an opaque architecture specified value. In Xtensa, it happens to be the stack pointer of the saved context. We save values onto the stack, so it just pushes whatever it needs to push onto the stack to save a context and returns a pointer to the bottom. And then, of course, you need to look at the value you got back. It may be, for example, basically there are two cases, right? The first one is the typical case. Nothing happened. It was a timer interrupt. It was just some GPIO thing. It didn't really change system state that much. You're still running the same thread, so we're going to return right into the thread we interrupted. And I actually mentioned most of this earlier. You don't actually need to do anything in this case to unspill anything. That happens out of the existing exception handlers that work just fine. So you just return up all the way into the assembly handling code that entered the interrupt in the first place, and then just go through about 5 or 6 instructions where we restore the EPC and the EPS registers that had been saved originally. Obviously, those went onto the stack, and then issue an RFI, return from interrupt instruction to return. And then it atomically then sets the PS and the PC, and then jumps back to user code. Because we don't actually use those exe save registers, we don't have no real need to return. Like if we take a priority 4 interrupt, we have no particular reason to use EPC4 and EPS4 to use the RFI. There's no particular reason in the hardware. The hardware doesn't care. We don't care. So we actually always use a single return path that just saves a couple bytes of code, which always uses the highest level. And the only reason we use highest level, in fact, the hardware doesn't seem to care at all. We could use any of them, except there is no EPC1 and an EPS1 because of the level 1 interrupts having a slightly different API historically. We could use any of them, but unfortunately, the QMU code gets confused. If you try to use a EPC register to return into code that is at a lower priority level than was interrupted. Again, hardware is fine with it because if you think about it, there's no reason for it to care. QMU then crashes. It was a fun bug to discover. But then there's the other case, right? Is that we're now returning from the interrupt and something has happened in the operating system and the currently running thread is different, right? Like it might have been a timer interrupt that woke up a high priority thread. It might have been IO that came in from network code that has woken up a meta IRQ thread for like bottom half processing, that sort of thing. We need to go somewhere else. Well, okay, now we're in a situation where we've got up thread caller stuff that belongs to the interrupted thread, to the old thread. It may still be in GPRs. It may never have been saved to the stack. Now we actually do need to spill all the frames. Sorry, use the right button there. So, well, okay, we've got to spill the frames. There's no real option here. It has to happen. Xtensa happily provides a HAL code, XD-HAL spill windows. That it's just a C function, and you call it, and when it returns, obviously your current function is still in GPRs, but everything else has been spilled. Only the 4 windows that are actually visible as GPRs right now are present in registers. It's actually pretty big. It's a couple hundred bytes of code. It's not super fast. It's something like 280 instructions. But it is software only, right? I mean, it does it via the straightforward manner that you really would expect, right? It reads the PS register, figures out what the call orientation is, because you can have big calls and small calls. Just enumerates all of them by looking at those bit masks in the PS register, and then plays a very complicated musical chairs game, because obviously as you're rotating the windows, the register numbers are changing underneath you, and so after the rot W, you need to then use a different number than before. And you can't rotate too far, because then you'll lose all the context you had, et cetera, et cetera. But nonetheless, they have code. It's pretty elegant. It does the right thing, and it works fine. We didn't use it. We wrote our own. The reason for that was just historical, because I had a rig when I was trying to figure out register window handling for Xtensa entry, or for Xtensa interrupt entry. I had a rig where I could go in and rotate the windows and touch a register and get it to spill, and then go check what happened and see that I understood it correctly and all of that. And it was a fairly straightforward thing to just evolve that into what if we just tried to go all the way around the circle, rotate a little bit, spill and again, you can see the code on the right-hand side of the screen here. You're right. I'm just touching something, like I'm anding a register with itself, because that's a no-op. And that seems like an easy thing to do, and it works with hardware to actually mutate the register and cause the exceptions to happen. Rotate a little and rotate a little and rotate a little. And the number of times you need to do it depends on how many registers are in the cycle, right? There can be 32 or 64. And this is tiny. I mean, if you look at it, what is it? It's like 12 instructions, or maybe a little less. And it actually is a lot faster, like almost twice as fast as doing the Xtensa code. The Xtensa code is a little optimized in that it will sit there and do less work if there are fewer registers to spill. But even then, so is this code, because if the registers aren't present, the exception handler won't do anything. It just won't trigger. So in fact, this beats it in all cases, and I was a little surprised by that. It turns out, basically, I mean, the end result is the hardware exception processing for register windows is actually really fast. The exception entry is fast. The exception code the Xtensa gives you is fast. And I don't think anyone told their software team, who then went and wrote the obvious implementation of this stuff. And the nice thing about having an architecture like this too is that you've got a straightforward rig for doing things like debugger integration, right? I mean, if you want to have a stack walker, you can't really walk the stack if you don't know whether the registers are on the stack or still in the GPR. So you need to be able to spill this on your own. So it's a nice trick to use there. Although there we are actually using the Xtensa HAL layer, and that's just because the stack walk code was contributed by Espressif, and I had written this, and we just never quite got together. But nonetheless, the Xtensa code still works just fine. There's no reason not to call it. It's just that for the interrupt exit case, where we really do care about performance, this happens to work a lot better. One difference here is that we actually rely on the exception handlers here, and therefore this code will not work if you disable exception processing, which is a possible CPU state in Xtensa, because exceptions are interrupts. You can actually mask that very highest level, and get a situation where, like, for example, divide by 0 won't trap and page faults won't happen and that sort of thing. I don't know that that's particularly useful, but if you do need to access to code like that, you do need to use the extensive version. All right, moving on. It's already 8:42. All right, I'm gonna move very quickly through SMP so I can talk about cache stuff, because cache stuff is actually the really important stuff. Xtensa is a routinely deployed in SMP configurations. ESP32 has 2 cores. The typical use case is not to use it in SMP, even though the hardware is capable. They actually tend to use the second CPU for dedicated Wi-Fi processing. But the Intel Audio DSP does. We've got 2 to 4 core configurations that are in hardware right now. And these are used for audio buffer passing and transformation, and even things like voice recognition. So the ability of an operating system to work on all of these different CPUs is actually kind of important. I will point out we don't have an MMU yet, which does simplify things. It was the first Zephyr SMP platform. I think I made that point earlier, which also means that most of our SMP mistakes stem from work on Xtensa, which is, so it's a little more rough than in, for example, the x86 code that came much later. So the SMP, you need to know what CPU you are. You need to know it fast, right? You need to have the current CPU struct, which has the current thread pointer, and you need the current thread pointer for basically everything in the kernel. So we use a dedicated state register for that. There are some requirements on this. When we get to being using an MMU, it has to be a privileged register. We can't have the user code going in and stomping on it, because that would be a security problem, obviously. We don't save it with context management, so it can't be like one of the GPRs. It's set once at boot, and then we leave it there. And Xtensa doesn't specify anything for this. We need to kind of come up with our own. And the first decision with ESP2 was to use this MISC register, which is great. It works perfectly, and it's not used for anything else because it's miscellaneous. Unfortunately, Intel didn't instantiate that. It's just not part of, again, configurable CPUs. They didn't have a MISC register. So we have a kconfig that basically tells us which register to use for this. And you notice we do use exesave too. It's one of those exesave registers that we don't otherwise use. It's kind of a nice advantage that we were frugal. We have some extra scratch space that we can scribble on when we need to. And I do have a question there. I think we've done this actually backwards. This is, again, it's a wart stemming from the first version, but it would actually be faster, I think, if we had a current thread pointer in the special register and access the CPU from that. There's an inherent race condition where you can get the current CPU, take an interrupt, switch to a different CPU, and then try to extract the current thread pointer, and you get the wrong thread because you're now on a different CPU. That we address that because we're always in an atomic context. We actually have to have a framework where we check. There's an assertion in the code that checks that we're in an atomic context when we get the current CPU pointer. And we wouldn't have needed that had we done it the right way. We also need an API for please start CPU number 1 or 2 or whatever. That's just part of the Arch layer. Obviously, you got to have it. Xtensa didn't do that. It's just not part of Xtensa. That's just not their architecture. It's left to the hardware integration to decide how to do that. There's a HAL call in ESP32 that isn't documented, but we cribbed some sample code from, I think it was the FreeRTOS integration. Actually, I forget what our reference was for the first version of this, and eventually kind of figured out how it worked. The Intel DSP actually doesn't have it at all. There's no way on the DSP to start up a CPU from scratch. The power management of these devices actually happens on the host CPU. So there's a driver protocol for bringing CPUs up and down that right now is extraordinarily primitive. We just bring them all up at startup, but that's not really long-term scalable because we do want to be able to change the CPU configuration at runtime. And we're kind of working this out with the Sound Open firmware folks right now as to what this needs to look like. It's sort of needlessly complicated because of both Xtensa and Intel decisions, but we'll figure it out. And then finally, there's a interrupt other CPUs API, ArchSched IPI, the interprocessor interrupt call. We do need this for scheduling. That's why it exists. You can have things that happen at runtime that change the set of runnable threads. That means that other CPUs need to be told about this because they might be running a low priority thread and have new work that they could run instead. There is no architectural interface for this at all. I think this is an even bigger hole that Xtensa left than it is with the start CPU thing, because this really is a kind of fundamental requirement, and the inability to do this means that everybody has to do it differently. With the Intel Audio DSP, there is a IPC, the interprocessor communication block of hardware with some, the doorbell style registers. There's nothing really particularly interested in them. Each pair of CPUs, like if you've got four CPUs, then each CPU has 3 registers to talk to each of the other CPUs to send them an interrupt, and then they can pass a single register of state along with the interrupt that the other side can then read, and then ACK, when it gets it, so that that you can then go on to do whatever it was you got. ESP32 just can't do it. There is no IPI on ESP32. That means that ESP32 needs to spin in its idle loop, waiting for the other CPU to receive an interrupt. Or not in its idle loop, excuse me. It needs to spin in its idle loop doing a yield, and it needs to spin waiting on the other CPU to get an interrupt when it does an IPI. At least not via a documented API. There were some comments we found in code that seemed to imply that such a thing exists, but we never managed to find docs for it or integrate it. Finally, missed it. There it is. Finally, you need atomic access to registers, to memory rather. And just like any other architecture, Xtensa has a compare and swap instruction that looks at the contents of a memory address, compares it to a value that the code believes is the old value, and if it is still the old value, will atomically write a new value on top of that. That way you can be sure that you were the person who changed it. Xtensa has the instruction that's S32C1I. I don't know what the one means. And I mentioned this earlier, there are only 2 operands for Xtensa instructions, and so the operand actually lives in this scompare register. And here I'm describing the subtle bug I did earlier, but yes, this is part of program state, and if you don't save this, you can take an interrupt where it gets it wrong. Now, this one we actually never saw in practice, because almost everywhere you're doing this, you're doing it with interrupts locked because you're somewhere in a kernel critical section. So this got fixed very late, but it is a bug, and there's nothing in Zephyr that requires the interrupts be locked in the atomic API. All right, so moving on, let's talk about cache. Again, Xtensa is used in a multi-CPU environment with shared access to a single memory, which means it can be contended. It might end up being slow. Different integrations are a bit different. The Intel Audio DSP, again, because it's instantiated on like modern logic processes, so it's a 400 megahertz plus CPU. It's really pretty fast. The SRAM bank has a little trouble keeping up. It has partly because of just its the CPU speed, but also there's a TLB translation lookup that allows a certain degree of memory management. This is something specific to this Intel DSP. And there are actually 2 different versions of SRAM on the device. There's a low-power SRAM that has significantly higher latency, and you can even touch system DRAM or a managed region of system DRAM, and that is really slow, like to the tune of like 70 cycles on the Xtensa side. So there is a CPU cache that Xtensa allows. Like everything else, it's configurable. The line size on these devices is 64 bytes. It is set associative. I believe it's a 3-way set associative on the devices that we're looking at. 16 kilobyte instruction data caches is a typical size. I mean, again, there's nothing unique to the architecture here. You've got dedicated instructions to do, write back and invalidate and flush, all of the regular cache control stuff that you would expect from any other architectures. And it's not coherent, which is from an operating systems perspective, kind of a disaster. I mean, everybody kind of learns about cache coherent stuff in school and sort of never really thinks they'll actually hit it. But here it really is true. And basically everything that you're thinking about by reading code breaks when you've got an incoherent SMP system. You can change memory from CPU 0, and it'll just stay in cache forever, and CPU 1 doesn't see it, right? That's what everybody kind of understands. But it also means that CPU 1 might have written stuff at some point in the past, gone on, and you've been looking at the old memory, and all of a sudden it gets flushed out on top of you, and you didn't see that coming. It just changes. Likewise, changing memory regions that you never touch, like it's only ever used from one CPU, but it happens to be in the same cache line as another device. Yeah, that can get clobbered too. The other CPU could have written the old version. You came in to use your variable, wrote a new version out. Old version gets clobbered on top of it. And even things where you're not actually colliding on cache lines, because the flush order is entirely stochastic. It's a essentially a random choice. There's probably an LRU within the CPU, but I don't know. But it's gonna pop out just at an essentially random order. Like it can be reordered in any way. So anything you had done inside of a spin lock, for example, might be predicated on the idea of this having been true then, but it actually was not true yet on that other CPU because it had already written to that. You just couldn't see it. Everything in the kernel, like just literally everything we do. I mean, the kernel is fundamentally about coordinating, things between threads. That's what the kernel is for. Assumes this universal visibility of a memory model, and so everything breaks. So we've got to fix this somehow. All right. So first thing we can try is don't fix it. Just disable the cache. Obviously, this guarantees correctness because now you're in an in-order memory environment and everybody's seeing the same memory. It actually works surprisingly well if the SRAM is fast relative to the CPU. ESP32 is like a 40 megahertz-ish device, and so is running at SRAM speeds. SRAM, I don't know if their accesses are one cycle or not, but they're close. And so ESP32, while it does have a cache available, actually does pretty well with this. I mean, you can get contended issues with memory, but it's really not too bad. But again, the audio DSP takes 12 cycles to read its fastest SRAM. It's just a non-starter. It needs the cache. If it doesn't have the cache, it's like running an order of magnitude slower. So idea number 2, and this I did play with a little bit. Harden the kernel, go into the kernel and try to fix things such that the kernel never makes a memory access in a context where it doesn't know the ordering and the state. And that's not as hard to do as you would think, because we have synchronization code already. We know when we're going to need to synchronize with another CPU. That's what a spin lock is. So do it then, right? When you're going to take a lock, flush your cache to make sure that the other CPU can see what it is you've been doing. While you're unlocked, that is. Invalidate your entire cache, right? Because now you need to be able to see what the other states are that are out there. So you can't use your copy of it. You need to know what's actually in memory the next time you touch memory. And then when you release the lock, flush, right? That means you're finished what you're doing, and before the lock is released, you do the flush so that everybody else can see it. Now, at the point where you've released the lock, they see everything you did before then correctly, and you see everything that was happened before you took the lock correctly. And this actually would work, I think. I never actually did it though, because if you think about it, it's really, really slow. So like non-synchronizing CPU-bound code is fast, right? If you're not trying to take synchronization things. 5 minutes left. All right, I'm going really behind here. If you're not trying to synchronize, then you're fast. Everything is great. But the kernel itself is synchronizing on everything. Again, that's what the kernel is for, is managing cooperation between preemptible threads. So in fact, the kernel's calls having to do all of this thread flush, this cache flushing ends up being much slower. Like spin locks go from a very lightweight abstraction to an extremely heavyweight abstraction. There is no, like, unfortunately, unlike x86 where it has just write back and validate instruction, there is no single instruction cache flush on Xtensa. You need to enumerate all the possible lines. So the naive version is 256 instructions. Some CPUs may have fewer lines, so you may be able to shave that down. Unfortunately, the DSP can't. It's 256 instructions to do that. So that's really slow. So that's not what we do either. So we went with idea number 3, config kernel coherence. This is a different memory model fundamentally, and it relies on one particular hardware trick that is specific to the audio DSP, but it's a trick that is really not specific to Intel at all. It's something almost anybody can do. Xtensa has a memory protection option. This is a very, very primitive MMU that allows you to associate cacheability and protection options with every 512 megabyte region of memory of address space differently. And so the Intel hardware basically maps the RAM twice. You got one in the cached region and one in an uncached region. So you can always get to stuff in an uncached way just by using the correct pointer, by offsetting it by 512 megabytes. And so the second trick is to recognize that almost everything the kernel stores, all the kernel data, is kind of always shared. There's really very little to gain by caching it, right? Like the CPU structs are all stuff that is shared between different systems. Thread records have priority values that need to be inspected from other CPUs. They've got linked list pointers that need to be enumerated. All of that stuff. Timeout objects need to be looked at from a timer interrupt that may happen on any CPU. IPC primitives, again, maybe you can do a semaphore give or take from any CPU. They're all designed to be used by anybody, and so there's no point in caching them. Just don't bother. Just put them in uncached memory. And that works because we've got the ability to change where that is. And next, you recognize that almost all stack accesses are intended to be unshared, right? I mean, like you're making function calls and you're going to return to that function on your current CPU. And the stack is almost all of actual code. Like almost all memory accesses are just touching the stack. They're looking at local variables. They're not looking at global stuff in typical code, right? So put the stack in cached memory. All right, that again is not hard, and we can in fact do this in the linker, right? We can define these coherent and incoherent attributes that just turn into section attributes that the linker can use to say, all right, enumerate all of the text and RO data segments, right? Those never get written to, therefore I can make them cached. Enumerate all over the user data segments. Those are modifiable. Let's make those uncached by default, because again, we want code to be correct by default, right? If the user wants to use the SOC API to get an uncached pointer to it, they're welcome to do so, but let's make it correct by default. And then here, let's enumerate all the stacks and make those cacheable. And this actually works really, really well. In fact, actually, performance looks basically identical between the single CPU cached case and the multi-CPU kernel coherence case. And the only problem, though, of course, is we've actually changed the rules, right? It's not impossible, and it's legal everywhere else to put a semaphore on the stack, to put a timeout on the stack, to do something like that. It's not legal anymore, not with kernel coherence, but it is in the rest of Zephyr. So there's a certain amount of coherence police that's going on right now in the code. We don't have a coherence platform in CI, or at least we don't yet. And so bugs with kernel coherence, tend to fester until someone runs the test suite on one of the DSP platforms, and I realize, oh yeah, okay, there's something on the stack. Most of the time in the test suite, we just move it. In a couple of cases, it's just the natural way to write the code. We don't want to change it, and we've just left it in place and used a filter to say that okay, that code won't run on the DSP. It just doesn't support it. And so, but there's some complexity here, right? And oh, I do see where can I have that access to the slides. I don't know what the official distribution is right now. This is just a Office 365 slide set in my OneDrive, and I will email the PowerPoint to Brett, I guess, whoever needs it. But just ask for it here. I will make sure everybody gets it. I'm sure the slides will be archived somewhere by the Zephyr team. Okay, great, thanks. But unfortunately, context switch gets kind of complicated in this case. All right, so remember the register windows? Well, okay, if you're going to make a context switch, now you actually do have to spill all your register windows, because again, your CPU may not be the next one to run this, and you can't have stuff on another CPU be sitting in GPRs. You need to flush out your old threads stack, right? You've made modifications to your stack. You need to flush it. You don't need to flush the bottom where you haven't touched it, right? Because you don't have any modified data there. But you do need to flush everything that's active, everything between your stack pointer and the top. You need to invalidate your copy of the new thread stack. And the reason is you may have run that thread in the past, right? It might have run on your CPU, but it might have most recently run somewhere else, and your copy may be stale. So you need to invalidate everything that you've got. And that means everything on the entirety of the thread. You don't need to invalidate the stuff below there, because since you're running on your CPU, it will clobber it before it tries to read it. And a fun bug here was Xtensa has it's a little like the x86 red zone. There's a region below the current stack pointer, which is a spill region for call errs. and the reasons for that have to do with the way the clever way that they've done register window handling. But it needs to be accounted for in your math about where the actual bottom of the stack is, because it's entirely possible to spill that into a cache line that didn't get flushed. That was a fun bug to fix, may I tell you. I will just say that cache incoherence, while it might have seemed like a great idea and saves a bunch of transistors on the CPU, is extraordinarily difficult. This is some of the hardest code I have ever made work, although I think we have it working now. If any of the people in the audience are ever in the process of designing a CPU, please don't do this to people. Like I said, I think we've gotten to a model where we've got code that will work and we've got some backstop checks to make it work. But it really is. This is not something I would ever want to push onto an application vendor. And having chatted with the folks who have written application code on these devices in the past, this has been a real problem. In fact, one of the big selling points about Zephyr, both within and without of Intel, is that we've actually made this work. I mean, we've got a story where we say, hey, we've got something to say about cache and SMP, and we can do that. And other operating systems, at least so far, haven't been able to. Well, other RTOSes. Again, there is a Linux port. And so and just getting to the last little bit there, you'll notice that there's an arch cohere stack call that we've added. It gets called out of the swap call and out of interrupt exit. And it's just a C function. It's called from C code. It's an inline function. You can't do it all in C though, because we're still running on our stack. We're still modifying things. We don't know what the compiler generated code is going to do. So it does almost all the logic required to compute the boundaries and stuff, but doesn't actually do the flush itself. What it does is it stashes the endpoint pointer in exe-save3. Remember that? We've got extra scratch registers that are available. And then in the assembly code, immediately before the context switch or the interrupt return, it will then do an enumeration and do the actual flush. There's some ideas for future optimization. I'm actually going to skip that since we are 4 minutes over. I apologize. And there's some slides at the end where I talk about memory management. This is future stuff. We don't have it working yet because we don't have hardware that needs it yet, but watch this space. Cadence provides both an MPU and an MMU, and both are, they have that very Xtensa-y, too clever for their own good kind of behavior, but they look really fun, and I think they're both going to work, and I think we're actually going to need to implement both. So like I say, watch this space. There may be some fun stuff coming along. And with that, I think I'm going to skip the last slide, and again, folks will be able to grab the slides after the fact, and those who I just found it's great use of the poet quote that captures exactly the the affect with which I think Xtensa was designed. And like I say, folks who need to find me, I am Andy Ross at both GitHub and Zephyr Project, or the Slack rather. So find me there. Find me via Intel, the Intel email address if you have questions. You can find by andy@plausible.org too if you're interested. But feel free to ask questions. And with that, like I say, we're 5 minutes over, and I don't know that there's time for questions. But if folks want to skip a meeting, I'm happy to stay on the line and answer them. And I apologize. I wasn't as far off on time as I was thinking I was going. I was afraid I might be, but a better run through might have tightened this up a bit.
Great. Are there any questions? Nope, just a lot of people thanking you.
Okay, hey, that's fine. I mean, folks have other talks to get to, and so do I. I can't remember what I wanted to go to next, but I will be rushing off to that.
Okay, thank you, everyone.
All right, great. Well, have fun all.